Imagine standing on a world where storms rage for centuries, where auroras light up the sky with colors unseen on Earth, and where secrets lurk beneath swirling clouds so vast they could swallow our planet whole. This isn't science fiction. This is Jupiter, the solar system's enigmatic giant, a planet so massive it reshaped the destiny of everything around it, yet so mysterious that even our most advanced probes have barely scratched the surface of its secrets. Today, we're diving into 25 of Jupiter's most baffling puzzles, from its ancient, shrinking storm, the Great Red Spot, to eerie electromagnetic whispers that scientists still can't explain. Some of these mysteries might even defy the laws of physics as we know them. So buckle up, because by the end of this journey, you'll see Jupiter not just as a distant gas giant, but as a cosmic riddle waiting to be solved. And who knows, one of these enigmas might hold the key to understanding not just Jupiter, but the very fabric of our solar system. Let's begin. Now, let's zoom in on the crown jewel of Jupiter's mysteries, the Great Red Spot. This isn't just any storm. Imagine a hurricane so vast it could swallow Earth whole, yet it's been churning for at least 400 years, possibly even longer. That's the Great Red Spot, a colossal tempest that defies everything we know about weather. But here's the twist: this iconic storm is changing, and no one's entirely sure why. For decades, astronomers watched the Great Red Spot shrink. Once wide enough to fit 3 Earths side by side, it's now barely wider than one. Even its color has shifted, morphing from a deep brick red to a pale salmon hue. Some researchers think these changes hint at the storm's eventual demise, while others believe it's simply evolving. The truth: Jupiter's atmosphere is a chaotic dance of forces we're still deciphering. What keeps this storm alive for centuries? On Earth, hurricanes fade once they hit land or cool waters. But Jupiter has no surface, just an endless ocean of hydrogen and helium. The Great Red Spot feeds off swirling jet streams that act like conveyor belts, pumping energy into the storm. Some theories suggest heat rising from Jupiter's core might play a role, while others point to smaller storms merging and reinforcing it. Yet none of these fully explain its stubborn persistence. And then there's the mystery of its color. The leading theory: sunlight breaking apart chemicals like ammonia and acetylene high in Jupiter's atmosphere, creating reddish compounds. But why the color shifts over time remains unanswered. Could it be tied to changes in the storm's depth or chemistry, or is something more exotic at work? The biggest question, though, is whether the Great Red Spot will vanish. Some models predict it could dissipate within our lifetimes, while others argue it might stabilize or even rebound. One thing's certain: as long as this storm rages, it will keep challenging our understanding of planetary atmospheres and reminding us just how little we truly know about the giant next door. Up next, we'll delve deeper into the Great Red Spot's shrinking act and what it reveals about Jupiter's hidden forces. Turning our attention to the Great Red Spot's puzzling transformation, let's examine the storm's shrinking behavior in greater detail. Over the past century, this colossal tempest has lost nearly half its size, condensing from a width that could once swallow 3 Earths to barely fitting one today. But the real intrigue lies not just in its diminishing size, but in the erratic pace of this decline. Sometimes it shrinks rapidly, other times it holds steady, as if resisting its own disappearance. So what's behind this slow unraveling? One compelling theory points to Jupiter's raging jet streams, rivers of wind that race at hundreds of miles per hour. These streams act like atmospheric walls, confining the Great Red Spot and potentially stealing its energy. Recent data suggests the storm might be getting squeezed by neighboring currents, gradually eroding its edges like a boulder worn down by a relentless river. But here's the catch: if this were the only factor, the shrinkage should be more consistent. Instead, the storm's unpredictable ebb and flow hint at deeper forces at work. Another possibility involves energy dissipation deep within the storm itself. Unlike Earth's hurricanes, which lose power when they encounter land or cold water, Jupiter's mega-storms churn in a fluid environment with no solid boundaries. Some scientists speculate that turbulent eddies within the Great Red Spot could be sapping its energy from the inside, causing it to slowly unravel. Imagine a spinning top that wobbles as it loses momentum, except this top is a 400-year-old tempest the size of a planet. Amateur astronomers have played a surprisingly vital role in tracking these changes. Equipped with backyard telescopes and high-resolution cameras, dedicated skywatchers have documented subtle shifts in the storm's shape and color, filling gaps between professional observations. In 2015, one amateur even captured a rare event, a massive blade of dark material spinning off the storm's edge, a phenomenon that later helped researchers model the storm's internal dynamics. These citizen scientists prove that unraveling Jupiter's mysteries isn't just the work of billion-dollar spacecraft sometimes. The key lies in the patient gaze of an enthusiast under a starry sky. The Great Red Spot's fate remains uncertain. Will it stabilize, vanish entirely, or even flare back to its former glory? Every observation adds a new piece to the puzzle, reminding us that Jupiter's atmosphere is a dynamic, living system, one that refuses to conform to our expectations. As we continue to watch this enigmatic storm, one thing is clear: its story is far from over. Coming up, we'll shift our gaze to another dazzling spectacle, Jupiter's auroras, which outshine Earth's northern lights in ways that defy explanation. Leaving behind the swirling chaos of the Great Red Spot, let's venture into one of Jupiter's most breathtaking phenomena, its otherworldly auroras. These aren't just scaled-up versions of Earth's northern lights. Jupiter's auroras are colossal, energetic displays that dance across its poles with a brilliance that dwarfs our planets, and they operate by rules that still baffle scientists. For starters, Jupiter's auroras are hundreds of times more powerful than Earth's. While our auroras shimmer gently in visible light, Jupiter's blaze in X-rays, a high-energy glow invisible to the naked eye but detectable by spacecraft like NASA Chandra X-ray Observatory. These X-ray auroras pulse with eerie regularity, flaring up every few dozen minutes like a cosmic lighthouse. But here's the twist: unlike Earth's auroras, which are driven primarily by solar wind, Jupiter's often flare up even when solar activity is calm. Something else must be fueling them. That something else lies in Jupiter's monstrous magnetic field, the strongest in the solar system after the Sun's. This magnetic field doesn't just guide charged particles. It acts like a high-voltage power line, accelerating particles to speeds so extreme they generate X-rays upon impact. But the real wild card in this celestial light show is Jupiter's volcanic moon, Io. Io spews out vast amounts of sulfur and oxygen ions, which get caught in Jupiter's magnetic grip and funneled toward the poles. When these particles collide with Jupiter's atmosphere, they unleash ultraviolet and X-ray auroras unlike anything seen elsewhere. The interplay between Io and Jupiter's magnetic field creates another bizarre effect: permanent auroral rings. On Earth, auroras shift with solar activity, but Jupiter sports glowing ovals around its poles that never fade, marking where Io's volcanic debris endlessly rains down. Even stranger, these auroras sometimes detach from their usual locations and skitter across the planet's atmosphere, as if tugged by invisible strings. Scientists suspect hidden electric currents or magnetic reconnection. A snapping and realigning of magnetic field lines might be behind these wanderings. Recent observations by the Juno spacecraft added another layer of intrigue. Juno discovered that Jupiter's auroras sometimes pulsate in unison with the planet's rapid rotation, suggesting a planetary-scale heartbeat linking its magnetic field, atmosphere, and even its deep interior. Yet other auroras flicker independently, defying any clear pattern. This unpredictability hints that Jupiter's auroras are more than just pretty lights. They're a window into the chaotic, unseen forces churning within the gas giant. What's next in this luminous mystery? Some researchers propose that Jupiter's auroras might even influence its weather, channeling energy into storms deep below. Others speculate about undiscovered processes in its magnetosphere, where particles race at near light speed. One thing's certain, as we unravel these radiant enigmas, Jupiter's auroras keep proving that the solar system's most dazzling light show is also its most perplexing. Up next, we'll dig into another puzzle lurking beneath Jupiter's colorful clouds, the mystery of its missing core. Now, shifting our gaze from Jupiter's dazzling auroras, we turn to a mystery buried deep within the planet itself, the enigma of its missing core. For decades, scientists assumed Jupiter, like other gas giants, harbored a solid, rocky heart at its center. But when NASA Juno spacecraft began peeling back the layers of Jupiter's atmosphere, it uncovered something utterly unexpected. The planet's core might not be dense and compact at all. Instead, it appears fuzzy, partially dissolved, or even scattered, defying everything we thought we knew about how gas giants form. The conventional model of Jupiter's formation suggested it started with a solid core of rock and ice, roughly 10 to 20 times Earth's mass. This core would have acted like a gravitational anchor, pulling in vast amounts of hydrogen and helium from the early solar nebula, eventually growing into the colossal planet we see today. But Juno's gravity measurements tell a different story. Rather than detecting a sharp, concentrated mass at Jupiter's center, the data reveals a diffuse, diluted core that blends gradually into the surrounding metallic hydrogen layer. It's as if the planet's solid heart has been stirred into a murky soup. So, what could have caused this? One leading theory is core erosion. The idea that Jupiter's intense pressure and heat might have slowly dissolved its rocky center over billions of years. Under the extreme conditions inside Jupiter, where temperatures soar to tens of thousands of degrees and pressures are millions of times greater than Earth's surface, even rock and metal could behave like a fluid. Heavy elements might have diffused upward, mixing with the planet's swirling metallic hydrogen and leaving behind only a vague, smeared-out remnant of the original core. Another possibility is a cataclysmic collision in Jupiter's early history. Imagine a rogue protoplanet, perhaps as massive as Earth, slamming into Jupiter at high speed. Such an impact could have shattered the core, scattering debris throughout the planet's interior. Over time, these fragments would have dispersed, creating the fuzzy boundary we see today. This scenario isn't as far-fetched as it sounds, after all. Jupiter's gravity makes it a cosmic magnet for wayward objects, as the comet Shoemaker-Levy 9 demonstrated in 1994 when it crashed into the planet in a series of spectacular fireballs. Yet another twist comes from planetary formation models, which suggest Jupiter might never have had a traditional solid core at all. Some simulations show that under certain conditions, gas giants could form directly from the collapse of a dense cloud of gas and dust, skipping the rocky core phase entirely. If true, Jupiter's core might simply be a region where heavier elements settled but never fully condensed into a solid mass. The implications of this mystery stretch far beyond Jupiter. If gas giants don't always form with distinct cores, it could rewrite our understanding of planetary systems across the galaxy. Even our own solar system's history might need revisiting. Perhaps Saturn, Uranus, or Neptune also hide similarly fuzzy cores. For now, Juno's data continues to puzzle scientists, leaving us with more questions than answers. As we prepare to leave the depths of Jupiter's interior, another puzzle lies in wait. One that twists the very fabric of the planet's magnetic field. Why is it so lopsided, and what does that tell us about the forces churning beneath those stormy clouds? Leaving the depths of Jupiter's enigmatic core behind, we now encounter another head-scratching feature of this gas giant, its bizarrely uneven magnetic field. Unlike Earth's relatively symmetrical magnetic shield, Jupiter's is a patchwork of intense and puzzlingly weak zones, defying the neat rules scientists once assumed governed planetary magnetism. NASA's Juno mission has been at the forefront of unraveling this mystery, revealing a magnetic landscape so irregular it's forced us to rethink how dynamos, the engines that generate magnetic fields inside planets, actually work. Earth's magnetic field is like a tidy bar magnet with clear north and south poles, but Jupiter's is anything but orderly. Juno discovered that the planet's northern magnetic hemisphere is wildly disorganized, with a chaotic cluster of strong and weak spots, while the southern hemisphere has a concentrated, almost jet-like stream of magnetic flux. One particularly odd feature, nicknamed the Great Blue Spot by researchers, is a localized region of intense magnetism near the equator, ironically. Not blue at all, but named for the color used to represent it in data models. This spot alone is stronger than anything Earth's magnetic field can produce, yet just a short distance away, the field weakens dramatically. What's causing this lopsidedness? The answer likely lies deep in Jupiter's interior, where swirling rivers of metallic hydrogen, a bizarre, electrically conductive form of hydrogen under extreme pressure, act as the dynamo generating the planet's magnetism. On Earth, our dynamo arises from molten iron circulating in the outer core, but Jupiter's dynamo is far more complex, possibly influenced by layers of different materials, turbulent flows, or even remnants of that fuzzy core we just explored. Some scientists speculate that Jupiter's magnetic asymmetry could stem from a shallow dynamo, where the magnetic field is generated closer to the surface rather than deep within the planet. Others propose that helium rain, drops of helium condensing and falling through the hydrogen layer, might disrupt the dynamo's flow, creating pockets of irregular magnetism. Juno's measurements also revealed another shock. Jupiter's magnetic field changes over time, something planetary scientists didn't expect to see on such a short timescale. Earth's magnetic poles drift and even flip over millennia, but Jupiter's field seems to be evolving within mere years. This volatility suggests the dynamo is highly sensitive to shifts in the planet's interior, perhaps due to storms or deep winds redistributing electrically conductive material. The implications of these findings stretch beyond Jupiter. Magnetic fields are cosmic shields protecting planets from harmful solar radiation. If a field is as uneven as Jupiter's, it could mean some regions of the planet are more exposed to space weather than others. This might explain why Jupiter's auroras, those dazzling light shows we discussed earlier, are so unpredictable and intense. It also raises questions about other gas giants. Could Saturn's hexagon or Neptune's wild winds be tied to similarly lopsided magnetic engines? As we piece together Jupiter's magnetic puzzle, another mystery drifts into view, one that's far wetter than scientists anticipated. Why does Jupiter, a planet named after the king of the Roman gods, seem to be lacking the very substance we associate with life, water? Now we turn our attention to a mystery that seems almost counterintuitive: Jupiter's disappearing water. This gas giant, named after the ancient god of sky and thunder, should be drenched in the stuff, yet scientists keep coming up short when they try to measure it. Early theories suggested Jupiter's atmosphere would hold vast amounts of water, similar to the abundance of oxygen and carbon found there. But when the Galileo probe plunged into Jupiter's clouds in 1995, it detected far less water than expected, only about 1/10 the amount scientists predicted. This was baffling. If Jupiter formed from the same solar nebula as the Sun, rich in oxygen, where did all that water go? One possibility is that the Galileo probe simply hit a dry patch. Jupiter's atmosphere is a turbulent sea of storms and jet streams, and water vapor might be unevenly distributed, pooling in deeper layers or hidden beneath thick clouds. Storms like the Great Red Spot could act like massive sponges, soaking up water and pushing it far below the visible cloud tops. Recent data from the Juno mission supports this idea, with microwave scans revealing signs of water deep in Jupiter's atmosphere, perhaps 10 times deeper than Galileo could measure. Another explanation takes us back to Jupiter's formation. Some planetary scientists argue that Jupiter might have formed farther from the Sun, in a colder region of the solar nebula where water ice was abundant before migrating inward. If that's the case, much of its original water could have been locked away in its core or chemically altered over billions of years. Alternatively, Jupiter might have gobbled up dry planetesimals' rocky building blocks as it grew, diluting its overall water content. There's also the chance Jupiter's water isn't missing at all, it's just in a form we don't fully understand yet. The planet's extreme pressures and temperatures could be forcing water molecules into exotic states like supersonic ice, where hydrogen atoms flow freely through a lattice of oxygen. If that's happening, our current instruments might not detect it the way we expect. This puzzle isn't just academic. Water is a key piece of the solar system's origin story, how planets form, how ingredients are distributed, and even where life could emerge. If Jupiter's water is hiding, it challenges our assumptions about the early solar system. And if it's truly scarce, we have to rethink how gas giants evolve. As we ponder Jupiter's elusive water, another striking feature comes into focus: the mesmerizing, perfectly arranged cyclones circling its poles, defying every rule we know about storm behavior. Now, let's shift our gaze to one of Jupiter's most mesmerizing and baffling features, its polar cyclones. When the Juno spacecraft arrived at Jupiter in 2016, it revealed something no one expected: perfectly arranged clusters of massive cyclones swirling around the planet's north and south poles. These storms aren't just random chaos, they form strikingly geometric patterns, a pentagon of cyclones in the north and an octagon in the south, as if etched by some invisible hand. Each of these cyclones is enormous, some spanning widths comparable to the entire United States. What's truly puzzling is how they behave. On Earth, storms of this size would either merge or dissipate due to friction and competing winds. But Jupiter's cyclones refuse to follow the rules. They spin relentlessly, maintaining their precise formations for years without drifting into one another. This defies every computer model and atmospheric theory scientists have tried to apply. So what's keeping these storms in place? One leading theory points to Jupiter's deep, churning atmosphere. Unlike Earth, where storms are surface-level phenomena, Jupiter's cyclones might be anchored by powerful currents far below the visible cloud tops. These deep winds could act like an invisible scaffolding, holding the storms in their geometric arrangements. Another idea suggests that the cyclones are trapped within jet streams that circle the poles, creating a sort of atmospheric racetrack that prevents them from colliding. Then there's the mystery of their energy source. On Earth, cyclones draw power from warm ocean waters, but Jupiter has no oceans. Instead, these storms might be fueled by heat rising from the planet's interior, combined with the constant churn of its dense, turbulent atmosphere. Some researchers even speculate that Jupiter's powerful magnetic field plays a role, interacting with charged particles in the atmosphere to stabilize the storms in ways we don't yet understand. The most intriguing possibility, though, is that we're seeing the fingerprints of a hidden process, something entirely new to planetary science. Jupiter's polar cyclones could be the result of exotic fluid dynamics that only occur under the planet's extreme pressures and temperatures, a phenomenon we've never observed anywhere else in the solar system. These cyclones aren't just curiosities, they offer a window into the deeper workings of gas giants, both in our solar system and beyond. If we can unravel why they behave the way they do, it could rewrite our understanding of how planetary atmospheres function. And as Juno continues its mission, each flyby brings us closer to answers, or perhaps to even bigger questions. With this celestial dance of storms still swirling in our minds, we turn next to another enigma: the astonishing speed of Jupiter's winds, which race faster than any hurricane Earth has ever seen. Now let's venture deeper into Jupiter's swirling chaos, where the winds defy everything we know about planetary atmospheres. Imagine a hurricane so vast it could swallow Earth whole, then multiply that by thousands. This is the scale of Jupiter's jet streams racing at speeds over 1,000 miles per hour. That's 3 times faster than the most violent hurricanes on our planet. But here's the real puzzle. On Earth, winds are slowed by friction from mountains, forests, and oceans. Jupiter has none of these, no solid surface, no terrain, just an endless abyss of churning gas. So how do these winds sustain such mind-bending speeds without burning themselves out? The answer might lie in the unimaginable depths of Jupiter's atmosphere. Recent data from the Juno spacecraft suggests these winds aren't just skin-deep. They might plunge thousands of miles downward, driven by forces we can barely comprehend. Think of it like stirring a cup of coffee, except the cup is 12 times wider than Earth, and the spoon is an invisible, planet-sized force. Some scientists believe Jupiter's rapid rotation, spinning once every 10 hours, acts as an engine, whipping the atmosphere into a frenzy that extends far below the visible cloud tops. Others propose that heat rising from Jupiter's scorching interior creates colossal convection currents, like a bubbling pot of cosmic soup, fueling these eternal winds. Then there's the bizarre phenomenon of shallow lightning. Unlike Earth's lightning, which originates deep within storm clouds, Jupiter's flashes appear to spark much higher in the atmosphere. Juno detected these eerie, high-altitude discharges, and they might hold a clue. The leading theory, ammonia, lots of it acting in ways that would make any chemist do a double take. On Jupiter, ammonia doesn't just dissolve in water like it does on Earth. At certain depths, it forms a slushy, exotic mixture with water vapor, creating electrically charged mushballs that soar upward on violent updrafts. When these mushy hailstones collide, they could generate the shallow lightning we observe, while also redistributing energy across Jupiter's atmosphere like a planetary-scale battery. But perhaps the most tantalizing possibility is that Jupiter's winds are powered by something even stranger, a hidden layer where hydrogen, under crushing pressures, becomes a metallic fluid. This molten ocean of conductive hydrogen could interact with Jupiter's monstrous magnetic field, creating currents that drive the winds from within. It's like the planet has its own built-in particle accelerator, churning out energy we're only beginning to detect. What makes these winds so extraordinary isn't just their speed or depth, it's their stability. Despite the chaos, Jupiter's jet streams have remained in roughly the same bands for centuries. There are no traffic jams in this atmospheric freeway, no crashes between rival winds. Somehow, this gas giant has found a way to balance unimaginable violence with eerie order, and we still don't know how. As we peel back the layers of this mystery, remember, Jupiter isn't just a planet. It's a laboratory for physics that doesn't exist anywhere else in our solar system. And with every new discovery, we're not just learning about Jupiter, we're rewriting the rules of planetary science itself. Up next, we'll confront a mystery that challenges the very laws of thermodynamics. Jupiter's unexplained heat, radiating more energy than it receives from the distant sun. Now let's turn our attention to one of Jupiter's most baffling quirks, its impossible energy budget. Picture this: the sun bathes Jupiter in sunlight, but the planet doesn't just reflect or absorb that energy. It radiates more heat back into space than it receives, like a cosmic furnace running on some hidden fuel source. For every bit of sunlight Jupiter catches, it throws out nearly 1.5 times that amount as its own infrared glow. This isn't just a minor discrepancy, it's a full-blown violation of the basic rules we expect from planetary physics. So where is all this extra energy coming from? One leading theory points to Jupiter's violent birth. When the planet formed 4.5 billion years ago, it likely started as a seething ball of gas and dust collapsing under its own gravity. That process would have generated staggering amounts of heat that could still be slowly leaking out today, billions of years later. Think of it like a freshly baked cake left to cool on the counter. Even hours later, if you touch the center, it's still warm. Jupiter might be doing the same thing, but on a planetary scale. The problem: calculations suggest this leftover heat should have dissipated by now. Jupiter's interior remains far hotter than this theory can explain, as if the cake never stopped baking. Then there's the curious case of helium rain. Deep inside Jupiter, where pressures reach millions of times greater than Earth's atmosphere, hydrogen, the planet's main ingredient, becomes a metallic liquid. Under these extreme conditions, helium, which normally mixes smoothly with hydrogen, might instead clump together like oil separating from water. These helium droplets would then rain downward through the metallic hydrogen, releasing gravitational energy as they fall. It's like dropping marbles into a vat of molasses. Each one generates a tiny burst of heat as it sinks. Over millennia, this process could theoretically warm Jupiter's interior. But while models show helium rain might contribute, it's unlikely to account for the sheer volume of excess energy we observe. Now, let's venture into the most speculative and controversial idea: nuclear reactions. On Earth, we associate nuclear energy with fission in reactors or fusion in stars. Could Jupiter's core harbor something similar? Some researchers have proposed that under its crushing pressures, deuterium, a heavy form of hydrogen, might undergo low-grade fusion, releasing steady trickles of energy. Others suggest pockets of radioactive elements like uranium or thorium, left over from the solar system's formation, could decay and heat the interior like a natural nuclear pile. But here's the catch: Jupiter's core temperatures, while scorching, are still far cooler than those required for sustained fusion, and radioactive decay, while plausible, struggles to match the planet's energy output. The biggest clue might lie in Jupiter's churning interior. Unlike Earth, where heat escapes primarily through conduction or volcanic activity, Jupiter's energy likely seeps out via convection, giant, slow-motion currents of rising and sinking gas. These currents could act like a planetary conveyor belt, dredging up heat from the depths over millennia. Combine that with the planet's relentless rotation, spinning so fast it flattens at the poles, and you have a natural stirrer, constantly agitating the atmosphere and redistributing energy in ways we're only starting to map. What makes this mystery so tantalizing is that it's not just about Jupiter. Similar energy imbalances have been spotted on Saturn and Neptune, hinting that gas giants might play by their own thermodynamic rules. Solving this puzzle could rewrite our understanding of how planets evolve, how they power their storms, and even how they influence the habitability of distant solar systems. As we wrestle with these questions, remember, Jupiter isn't just defying expectations. It's teaching us how much we don't know about the universe's most common planets. Up next, we'll unravel the secrets of Jupiter's faint but fascinating ring system, a cosmic whisper compared to Saturn's dazzling belts. Moving beyond Jupiter's enigmatic energy secrets, let's shift our gaze to something far subtler yet equally intriguing: its delicate ring system. While Saturn's dazzling rings steal the spotlight, Jupiter's own rings are so faint they weren't even discovered until 1979, when the Voyager 1 spacecraft captured them by sheer accident. Unlike Saturn's icy, glittering bands, Jupiter's rings are wispy and ghostly, made mostly of microscopic dust particles so tiny they'd vanish in a gust of wind here on Earth. So how did these ethereal rings form? The leading theory points to Jupiter's small inner moons like Metis and Adrastea. These moons are constantly bombarded by micrometeoroids, space dust, and tiny rocks hurtling through the solar system. When these particles smash into the moons, they kick up clouds of debris, which then get swept into orbit around Jupiter. Imagine throwing a pebble into a dusty attic. The impact sends particles flying, only for them to settle into a hazy, floating layer. That's essentially what's happening around Jupiter, but on a cosmic scale. Here's where things get puzzling. Scientists once predicted Jupiter's rings should be far more substantial, given the planet's powerful gravity and the sheer number of moons it has to supply debris. Yet the rings remain whisper-thin, suggesting some unseen process is at work. One possibility is that Jupiter's immense magnetic field acts like a cosmic vacuum cleaner, pulling charged dust particles out of orbit and into the planet's atmosphere. Another clue lies in the ring's odd structure. Unlike Saturn's neatly divided rings, Jupiter's system includes a bizarre halo ring, a faint donut-shaped cloud of charged particles that stretches far above and below the main rings. This halo glows with a ghostly blue hue, likely caused by interactions between the dust and Jupiter's radiation belts. The rings also hold surprises in their motion. While Saturn's rings orbit in an orderly flat plane, Jupiter's dust bands are tilted and wobbly, likely nudged by the planet's uneven gravity and magnetic quirks. Even stranger, the main ring isn't uniform. It's brighter and thicker near its inner edge, then fades dramatically outward, a pattern that hints at unseen forces, perhaps even tiny, undiscovered moons shepherding the dust into uneven clumps. What makes Jupiter's rings so fascinating isn't just their faintness, but what they reveal about the planet's hidden dynamics. They're a testament to the delicate balance between creation and destruction in space, where impacts birth new structures while gravity and magnetism whisk them away. And they remind us that even the quietest corners of our solar system can hold profound mysteries. Next, we'll dive into another electrifying puzzle, Jupiter's lightning, which crackles in places and ways that defy everything we know about storms on Earth. Now let's turn our attention to one of Jupiter's most shocking mysteries, its lightning. If you think Earth's thunderstorms are intense, Jupiter's lightning will make them seem like a sparkler in comparison. These aren't just flashes in the clouds, they're monstrous bolts up to 3 times more powerful than anything on our planet, and they crackle in places that leave scientists utterly baffled. On Earth, lightning is born in water-rich clouds, usually near the equator where warm, moist air rises, but Jupiter's lightning laughs at these rules. It erupts near the poles, far from the planet's stormy equatorial belts, and it's far more frequent, sometimes flashing dozens of times per second. NASA's Juno spacecraft even recorded lightning dancing over Jupiter's North Pole, a region once thought too cold and stable for such violent displays. So what's fueling these electrical tantrums? The answer might lie in something called mushballs, a bizarre form of hail unique to Jupiter. Picture this: deep in Jupiter's atmosphere, where temperatures and pressures are extreme, ammonia acts like antifreeze, mixing with water to create a slushy, semi-liquid mixture. When this slush gets caught in Jupiter's fierce updrafts, it freezes into icy chunks, but not like the hailstones we know. These are mushy, half-solid blobs packed with ammonia and water, tumbling through the clouds like electrified snowballs. As they collide and fracture, they generate staggering amounts of static charge, sparking lightning that's not just stronger than Earth's, but fundamentally different. Here's where it gets even stranger. While Earth's lightning tends to strike downward, Jupiter's bolts often shoot upward, starting deep in the clouds and arcing toward space. Some researchers think this reverse lightning might be tied to Jupiter's missing water. Measurements show far less water in Jupiter's upper atmosphere than expected, and one theory suggests mushballs are dragging it all downward, hiding it beneath the clouds where we can't see it. Every time a mushball forms, it acts like a watery sponge, soaking up moisture and pulling it into Jupiter's depths along the way, creating the perfect conditions for more lightning. But the biggest puzzle isn't just how Jupiter's lightning forms. It's why there's so much of it. Lightning requires instability, rapidly rising air, clashing temperatures, and turbulent winds. Jupiter's poles, where much of this lightning thrives, were once thought to be relatively calm. Yet Juno's data reveals a hidden chaos, with cyclones and whirlpools churning beneath the ammonia haze. Some scientists suspect these polar storms act like giant batteries, continuously generating the friction needed to keep the lightning coming. Others wonder if Jupiter's lopsided magnetic field, which funnels energy toward the poles, is supercharging these storms beyond anything we've imagined. One thing's certain, Jupiter's lightning isn't just a scaled-up version of Earth's. It's a window into the planet's secret weather systems where familiar rules don't apply, and where even something as ordinary as a raindrop becomes alien. Every bolt cracks open new questions about how energy moves through a planet without a solid surface, and how storms can rage in places that defy logic. Up next, we'll unravel the palette of Jupiter's swirling storms, where the colors aren't just beautiful, they're a code waiting to be cracked. Now let's dive into the swirling canvas of Jupiter's atmosphere, where the planet's vibrant colors paint a mystery as deep as its storms. If you've ever gazed at images of Jupiter, you've seen its striking bands of cream, orange, brown, and blue, along with the occasional splash of red like the Great Red Spot. But here's the twist: scientists still can't fully explain what creates this dazzling palette. Ammonia and sulfur give us some clues, but they don't account for the full spectrum of hues that dance across Jupiter's clouds. Take Jupiter's famous white zones, for example. These bright, high-altitude clouds are mostly made of ammonia ice, which reflects sunlight brilliantly. But just below them lie the darker belts, where deeper clouds of ammonium hydrosulfide and water create richer browns and tans. That much makes sense. The real puzzle begins with the bursts of red and blue, colors that shouldn't exist if Jupiter's chemistry were as straightforward as we once thought. One leading theory points to radiation specifically, the brutal onslaught of ultraviolet light from the sun and cosmic rays from deep space. These high-energy particles could be breaking apart molecules in Jupiter's upper atmosphere, triggering complex chemical reactions that produce colorful compounds we haven't even identified yet. Think of it like a cosmic art studio where radiation acts as the brush, splashing unexpected pigments across the clouds. Some researchers suspect compounds called chromophores, molecules that absorb specific wavelengths of light, are responsible, but no one knows exactly which ones are at work. Then there's the role of Jupiter's relentless storms. The planet's jet streams, some reaching speeds of 1,000 miles per hour, churn the atmosphere like a giant mixer, dredging up material from deep below and exposing it to sunlight and radiation. This constant upheaval might explain why some regions suddenly darken or brighten over time. For instance, the Great Red Spot's iconic hue has shifted from brick red to pale salmon in recent years, a change that could be tied to rising or sinking gases altering the chemistry at play. But the plot thickens when we consider exotic compounds that might only form under Jupiter's extreme conditions. Lab experiments suggest that phosphorus or even organic molecules like acetylene could react with ammonia or hydrogen sulfide to create reddish tints. Some scientists speculate that Jupiter's deep atmosphere, where pressures are crushing and temperatures soar, could be brewing substances we've never seen on Earth, compounds that rise to the surface and paint the clouds in surreal shades. What makes this mystery even more intriguing is that Jupiter's colors aren't just for show. They're a map of the planet's hidden activity. Darker spots might mark regions where gases are surging upward from the depths, while lighter areas could signal where cold, reflective clouds dominate. And those rare blue patches near the poles, they might be thin, high-altitude hazes scattering sunlight the same way Earth's sky does, giving us a glimpse of the complex layers at work. So why haven't we cracked the code yet? Part of the challenge is that Jupiter's atmosphere is a moving target. Unlike Earth, where chemicals are relatively stable, Jupiter's turbulent weather constantly reshuffles the deck, making it hard to pin down which reactions are happening where. Missions like Juno are helping, but every new image seems to add another piece to the puzzle without giving us the full picture. As we peel back the layers of this chromatic enigma, one thing becomes clear: Jupiter's colors are more than just pretty swirls. They're fingerprints of the planet's inner workings, clues to the forces that shape its wild weather. And just like an unfinished masterpiece, Jupiter keeps adding new strokes, daring us to figure out what they mean. Coming up, we'll tackle another head-scratcher: why Jupiter, the oldest planet in the solar system, grew so massive while others stayed small. The answer might rewrite what we know about planetary evolution. Now, let's shift our gaze to a mystery that isn't just about what Jupiter looks like, but how it got so impossibly big in the first place. Jupiter's sheer size is a cosmic anomaly. It's not just the largest planet in our solar system, it's more massive than all the other planets combined. But here's the real puzzle. Jupiter was one of the first planets to form, emerging from the swirling disk of gas and dust around the young sun. So how did it grow so much larger than everything else? The answer might rewrite the story of our solar system's birth. One leading theory suggests Jupiter had a head start. In the chaos of the early solar system, it may have gobbled up vast amounts of material before other planets could even take shape. Imagine a competitive eater at a buffet, clearing the table before others get a chance. Jupiter's core, whether solid or fuzzy, could have pulled in surrounding gas at an astonishing rate, ballooning to its current size in just a few million years. Some models even propose it migrated inward early on, vacuuming up extra material before settling into its current orbit. But there's a rival idea. Jupiter didn't just grow fast, it actively stunted its neighbors. Its immense gravity might have disrupted the flow of material to the inner solar system, starving planets like Earth of building blocks. Think of it as a cosmic bully hogging the playground swings. Evidence for this comes from asteroid belts and the odd sizes of Mars and Mercury, which are smaller than expected. Without Jupiter's interference, we might have had a very different lineup of planets today. What's even wilder is Jupiter's role as the solar system's architect. Its gravity likely shaped the orbits of other giants like Saturn and Uranus, and may have flung icy debris outward to form the Kuiper belt. Some scientists believe it even acted as a shield, hurling dangerous comets away from Earth, though others argue it occasionally sends them our way. This planetary puppet master didn't just grow big, it dictated the rules for everyone else. Yet mysteries remain. Why didn't Jupiter keep growing into a star? It's mostly hydrogen, just like the Sun, but it fell short of the mass needed to ignite fusion. And why are some exoplanets in other systems even larger, despite their stars being younger? Jupiter's size might be a clue to a universal recipe for planet formation, one we're still deciphering. As we marvel at Jupiter's dominance, remember, its size isn't just a record-breaking fact. It's a window into the solar system's turbulent youth, where one planet's rise shaped the destiny of all the others. Next up, we'll tune into Jupiter's strange radio signals, a symphony of cosmic noise that sounds anything but natural. Now, let's tune into one of Jupiter's most electrifying mysteries, its otherworldly radio signals. These aren't your average static or cosmic background noise. Some of these emissions sound like something straight out of a sci-fi movie, with eerie whistles, sharp cracks, and even pulses resembling laser blasts. Scientists have nicknamed them space lasers, but the truth behind these signals is even stranger than fiction. At the heart of this phenomenon is Jupiter's monstrous magnetic field, the strongest of any planet in our solar system. This magnetic field doesn't just sit there, it's alive with activity, especially where Jupiter's volcanic moon Io comes into play. Io, spewing tons of sulfur dioxide into space, creates a donut-shaped trail of charged particles around Jupiter. As these particles get caught in Jupiter's magnetic grip, they generate intense electrical currents, which in turn produce bursts of radio waves. These are the decametric radio emissions, and they're some of the most powerful natural radio signals in the solar system. But here's where it gets unpredictable. Unlike Earth's auroras, which follow a relatively steady rhythm tied to solar activity, Jupiter's radio bursts seem to have a mind of their own. Some are sporadic, firing off without warning, while others pulse in strange, repeating patterns. Scientists can sometimes predict when these signals will strengthen, like when Io passes through specific regions of Jupiter's magnetic field, but even then, the exact timing and intensity remain a guessing game. It's as if Jupiter has its own celestial radio station, and it refuses to stick to a schedule. What's even more puzzling is that some of these signals defy conventional explanations. Certain bursts, like the millisecond radio spikes, are so brief and intense that they resemble artificial transmissions. Could there be some unknown natural process amplifying these signals, or is there a deeper interaction between Jupiter's magnetic field and its moons that we haven't uncovered yet? The more we listen, the more questions arise. These radio emissions aren't just a curiosity, they're a window into Jupiter's hidden dynamics. By studying them, scientists hope to unravel the complex dance between Jupiter's magnetic field, its moons, and the charged particles swirling around them. Yet, for all we've learned, Jupiter's radio symphony remains a captivating enigma, reminding us that even in our own cosmic backyard, there are still signals we can't quite decode. Up next, we'll explore another striking feature of Jupiter's turbulent atmosphere, the mesmerizing string of pearls, a lineup of storms as beautiful as they are mysterious. Now, let's turn our gaze to one of Jupiter's most visually stunning mysteries, the string of pearls. Picture a necklace of massive white storms, each as wide as the continental United States, strung together in a near-perfect line along Jupiter's southern hemisphere. This breathtaking formation isn't just a temporary fluke. It's a recurring feature, appearing in the same latitude band every few years like clockwork. But what keeps these storms so perfectly aligned, and why do they resist merging into one colossal tempest like the Great Red Spot? The string of pearls owes its name to the way these oval-shaped storms gleam against Jupiter's darker cloud bands, resembling luminous beads on a cosmic thread. Unlike the chaotic turbulence seen elsewhere on Jupiter, these storms exhibit a strange order, maintaining their spacing and structure for years at a time. Scientists first spotted them in the 1990s, and since then, they've reappeared in cycles, suggesting something deep within Jupiter's atmosphere is orchestrating their formation. One leading theory points to atmospheric waves, massive disturbances rippling through Jupiter's gaseous layers. These waves, possibly generated by heat rising from the planet's interior, could act like invisible guide rails, funneling storms into specific latitudes. Imagine tossing pebbles into a stream. The ripples they create can influence where floating leaves gather. Similarly, these deep-seated waves might herd Jupiter's storms into neat, repeating patterns. Data from NASA Juno spacecraft supports this idea, revealing jet streams and vortices interacting in ways that could sculpt the pearls into their iconic lineup. But there's another twist. Some researchers suspect hidden structures beneath Jupiter's clouds are playing puppet master. Just as Earth's mountains and valleys steer weather systems, Jupiter might have unseen layers of dense, swirling fluid that channel storms along fixed paths. These hidden forces could explain why the pearls avoid colliding despite being packed so closely together. It's as if an invisible hand keeps them dancing in formation, never letting them stray too far or get too close. The stability of these storms is equally puzzling. On Earth, hurricanes dissipate after hitting land or cooler waters, but Jupiter has no solid surface to break them apart. Yet the pearls persist, some for decades, without growing or shrinking dramatically. This suggests they're tapping into a steady energy source, perhaps heat rising from Jupiter's interior or interactions with surrounding jet streams. Whatever the fuel, it's clear these storms operate by rules we're only beginning to decipher. What makes the string of pearls even more fascinating is how it contrasts with Jupiter's other storm systems. While the Great Red Spot dominates with its sheer size and longevity, the pearls showcase precision and repetition, offering a different window into the planet's turbulent heart. Studying them could unlock secrets about how energy flows through gas giants, not just in our solar system but across the cosmos. As we marvel at this celestial jewelry, one thing is certain: Jupiter's atmosphere is far more than a chaotic swirl. It's a dynamic, layered system where order and chaos intertwine in ways we're just starting to understand. Next up, we'll dive into another high-speed mystery: the jet streams racing around Jupiter at unimaginable speeds and why they don't tear the planet apart. Now, shifting gears from Jupiter's mesmerizing storm formations, let's zoom in on another jaw-dropping spectacle: the planet's hypervelocity winds. Imagine winds so fierce they could race from New York to Los Angeles in less than 3 hours. Jupiter's jet streams scream across its atmosphere at a staggering 1,000 miles per hour, making Earth's most violent hurricanes seem like gentle breezes in comparison. But how does a planet with no solid surface sustain such relentless, organized wind speeds without tearing itself apart? Unlike Earth, where mountains and oceans disrupt wind patterns, Jupiter's jet streams seem to glide effortlessly, maintaining their blistering pace with eerie stability. These rivers of gas, some wider than our entire planet, carve through the atmosphere in alternating band stripes of eastward and westward flow that have baffled scientists for decades. The real puzzle isn't just their speed, but their precision. Why don't these winds spiral into chaos, collapsing into turbulence like a stirred pot of boiling water? One school of thought suggests these winds are skin-deep, confined to Jupiter's upper cloud layers. Proponents argue that sunlight heating the ammonia-rich clouds could drive shallow circulation, much like how Earth's trade winds are steered by solar energy. But here's the catch: Jupiter's winds don't weaken at night, and their energy appears to dwarf what sunlight alone could provide. This has led others to suspect the winds run far deeper, possibly thousands of miles into the planet's interior, tapping into Jupiter's own heat reservoir. Data from the Juno spacecraft tipped the scales toward the deep winds theory. By measuring Jupiter's gravity field, Juno revealed that the jet streams might extend down to where immense pressures turn hydrogen into a bizarre metallic fluid. In this alien layer, electrical currents and magnetic forces could act like cosmic lubricants, allowing the winds to maintain their velocity without friction. Picture a planetary-scale engine with Jupiter's rotation and internal heat driving winds that stretch from the cloud tops to the abyss below. Yet even this explanation leaves gaps. If the winds are so deep, why do they follow such straight, narrow paths instead of swirling wildly? Some researchers point to Jupiter's rapid rotation. A day lasts just 10 hours as the invisible hand keeping the winds in check. Coriolis forces, the same effect that twists Earth's hurricanes, might corral Jupiter's jet streams into orderly lanes, preventing them from straying off course. Others speculate that the planet's magnetic field, the strongest in the solar system, interacts with charged particles in the atmosphere to stabilize the flows. The absence of turbulence is another head-scratcher. On Earth, winds at different speeds colliding create choppy, unstable weather. But Jupiter's jet streams, despite their velocity differences, seem to coexist peacefully, like parallel highways with no crashes. One tantalizing idea is that the planet's lack of a solid surface removes the brakes that normally disrupt airflow. Without mountains or continents to grind against, the winds might simply glide past one another, their energy dissipating gradually through subtle waves rather than violent clashes. What makes these winds even more extraordinary is their longevity. While Earth's jet streams shift with the seasons, Jupiter's have persisted for centuries, perhaps since the planet's formation. This suggests they're not just weather phenomena but fundamental features of Jupiter's structure, as integral to the planet as its iconic stripes. Understanding them could rewrite textbooks on fluid dynamics, offering clues about how gas giants across the universe manage their ferocious energies. As we grapple with these questions, one thing becomes clear: Jupiter's winds are more than just fast. They're a masterclass in planetary physics, challenging our assumptions about how atmospheres work. Next, we'll explore another celestial enigma, Jupiter's uncanny ability to capture passing objects, turning them into temporary moons with a gravitational sleight of hand. Now, let's turn our attention to one of Jupiter's most fascinating tricks, its gravitational artistry, the power to snatch passing objects and turn them into temporary moons. Picture Jupiter as a cosmic sculptor, reshaping the solar system with its immense gravity, bending the paths of asteroids and comets to its will. This moon-making power isn't just theoretical. Back in 1994, the world watched as comet Shoemaker-Levy 9, torn apart by Jupiter's gravity, plunged into the planet's atmosphere in a fiery spectacle. But before its dramatic end, it orbited Jupiter for decades, a captive of the giant's pull. This wasn't a one-time event. Jupiter's history is littered with similar captures, asteroids and comets briefly becoming part of its entourage before either escaping or meeting a fiery demise. What's intriguing is the inconsistency. Some captured objects, like the asteroid 2006 RH120, stick around for centuries, locked in stable orbits. Others, like Comet P209 Linear, vanish within years, slingshot back into space. Why the difference? It all comes down to timing and trajectory. Objects entering Jupiter's gravitational sphere at just the right angle and speed can settle into long-term orbits, almost like cosmic Parker athletes sticking the perfect landing. Those arriving at sharper angles or higher speeds might get a temporary tour before being ejected, as if Jupiter's gravity is a revolving door rather than a trap. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, get most of the attention, but the planet currently hosts at least 79 smaller moons, many of which are likely captured asteroids. Their orbits are chaotic, often retrograde, meaning they move opposite to Jupiter's rotation. This backward motion is a telltale sign of capture, as objects born from the same disk of material as the planet would orbit in the same direction. The process isn't just about brute force. Jupiter's immense gravity can gently tweak an object's path over time, nudging it into a stable orbit through a delicate dance of gravitational forces. Some researchers even speculate that Jupiter might share captured objects, handing them off to Saturn or flinging them toward the inner solar system. This could explain why some near-Earth asteroids have orbits that hint at a past encounter with the gas giant. Looking ahead, Jupiter's moon-making factory isn't shutting down. Astronomers predict future captures, especially from the Kuiper belt and the Trojan asteroid swarms that orbit ahead of and behind Jupiter. These captures could teach us more about the early solar system, as many of these objects are pristine remnants from its formation. What makes Jupiter's moon-making power so extraordinary is its role in shaping not just its own system, but the solar system at large. By capturing or redirecting asteroids and comets, Jupiter acts as both a shield and a disruptor, influencing the flow of material across space. This gravitational puppetry reminds us that planets aren't just passive objects, they're dynamic players in an ever-evolving cosmic drama. Next, we'll dive into another electrifying mystery, the plasma torus, a donut-shaped ring of charged particles encircling Jupiter, fed by the volcanic fury of its moon Io. Now, imagine stepping into an invisible force field that stretches millions of miles into space, a swirling, electrified donut wrapped around Jupiter. This is the plasma torus, one of the most dynamic and puzzling features of the Jovian system. Unlike anything seen around other planets, this ring of supercharged particles is fueled by the relentless volcanic eruptions of Jupiter's moon Io, creating a celestial power plant that shapes the planet's entire magnetic environment. At the heart of this phenomenon is Io, the most volcanically active world in our solar system. Its surface is dotted with hundreds of fiery vents, spewing sulfur dioxide and other gases high into space. Jupiter's immense gravity then rips these particles away, ionizing them into a soup of electrons and ions. This charged material gets trapped along Jupiter's magnetic field lines, forming a glowing, donut-shaped band around the planet. What's astonishing is the scale. This torus is so dense that if it were visible to the naked eye, it would appear wider than the full moon in Earth's sky. But why doesn't this plasma just drift away? The answer lies in Jupiter's magnetic grip. The planet's field is 20,000 times stronger than Earth's, acting like an invisible cage that herds the particles into a stable ring. Yet, this isn't a static structure. The torus pulses with energy influenced by Io's ever-changing volcanic activity. When a major eruption occurs, the density of the torus can spike dramatically, sending ripples through Jupiter's magnetosphere. This plasma donut isn't just a cosmic curiosity, it's a key player in some of Jupiter's other mysteries. For starters, it supercharges the planet's already intense auroras. While Earth's northern lights are powered by particles from the solar wind, Jupiter's auroras draw energy from the torus. As the plasma spirals along magnetic field lines, it generates electric currents that ignite dazzling light shows near the poles, some glowing in X-rays far more energetic than anything on Earth. The torus also plays a surprising role in Jupiter's bizarre radio emissions. Those eerie sounds, sometimes likened to lasers or ocean waves, are born from the interaction between the plasma and Jupiter's magnetic field. As electrons in the torus accelerate, they produce radio waves that can be detected across the solar system. These emissions aren't just noise, they're a window into the torus's ever-shifting dynamics, helping scientists track changes in Io's volcanic output or fluctuations in Jupiter's magnetic field. What's truly mind-bending is how this system operates like a giant electrical circuit. Io acts as a generator, the plasma torus serves as a conductive wire, and Jupiter's poles complete the loop. The energy flows in a continuous cycle with the torus acting as the middleman. This setup is so efficient that if you could harness it, the torus alone could power all of Earth's electrical needs, though the engineering challenges would be, well, astronomical. Yet the torus isn't perfectly stable. Solar wind buffeting, shifts in Io's volcanic activity, and even the gravitational tugs of other moons can distort its shape or alter its density. Sometimes, parts of the torus even split into distinct strands, like a frayed ribbon, before merging back together. These quirks make it a live laboratory for studying plasma physics, offering insights into everything from nuclear fusion to the behavior of distant exoplanets. As we peer deeper into this electrified halo, one thing becomes clear. Jupiter's plasma torus isn't just a byproduct of volcanic chaos. It's a cosmic conductor orchestrating some of the planet's most spectacular phenomena. From auroras that defy earthly comparisons to radio signals that puzzle astronomers, this swirling ring proves that even in the vacuum of space, energy finds a way to flow. Next, we'll uncover another thermal oddity, Jupiter's so-called hot shadows, where sunlight isn't the source of heat, and the rules of atmospheric warming seem to flip upside down. Now, shifting our gaze to another baffling discovery, we encounter Jupiter's mysterious hot shadows, a phenomenon that turns our basic understanding of planetary heating upside down. Typically, when we think of shadows, we imagine cooler, darker areas shielded from the sun's rays. But Jupiter, true to its reputation for defying expectations, flips this logic on its head. Thanks to NASA's Juno spacecraft, scientists have identified regions in Jupiter's shadowed zones that are actually warmer than their sunlit counterparts. This isn't just a minor anomaly. It's a direct challenge to how we think energy moves through planetary atmospheres. So, what's going on here? One leading theory points to Jupiter's colossal auroras. These aren't just pretty light shows, they're titanic energy factories. Charged particles from Io's plasma torus slam into Jupiter's poles, generating intense heat that doesn't just stay put. Instead, this heat seems to ride atmospheric waves, spreading outward and downward, even reaching areas hidden from sunlight. Imagine a cosmic game of hot potato, where energy from the poles gets tossed across the planet, warming places that should logically be cooler. It's as if Jupiter has its own hidden heating system, completely independent of the Sun. But auroras might not be the full story. Another possibility involves Jupiter's deep atmospheric winds, which can exceed 1,000 miles per hour. These jets could act like planetary-scale conveyor belts, redistributing heat from the equator to the poles and even into shadowed regions. On Earth, ocean currents and wind patterns help balance temperatures globally, but Jupiter's version operates on a staggering scale, with forces so powerful they might override the usual rules of solar heating. There's also speculation about internal heat sources, like the slow contraction of Jupiter's core or the friction from its differentially rotating layers. If this heat rises unevenly, it could create localized warm spots even in darkness. The implications are profound. If shadows can be hotter than sunlit zones, it means Jupiter's atmosphere doesn't behave like anything in our textbooks. Conventional models built on Earth's relatively placid climate struggle to explain how energy zigzags so unpredictably across Jupiter's gaseous expanse. This isn't just about Jupiter either. Gas giants like Saturn or exoplanets light years away might operate by similar rules, forcing us to rethink how planetary climates evolve. Juno's data has added another twist. These hot shadows aren't random. They appear most often near the poles, aligning with auroral activity, but they've also been spotted at lower latitudes, defying easy categorization. Some scientists wonder if Jupiter's immense magnetic field plays a role, channeling energy in ways we can't yet map. Others suggest that exotic chemistry, like the breakup of molecules by radiation, might release heat in unexpected pockets. One thing's certain, Jupiter's hot shadows are more than a curiosity. They're a glimpse into the chaotic, high-energy dance of a gas giant's atmosphere, where the sun isn't always the main driver of temperature. As Juno continues its mission, each flyby peels back another layer of this mystery, revealing just how little we truly understand about the giants of our solar system. Up next, we'll tackle another head-scratcher: why Jupiter's storms seem to skip a size category, with no middle ground between tiny eddies and colossal vortices. Now, let's turn our attention to another puzzle in Jupiter's turbulent atmosphere, the curious case of its missing medium-sized storms. Jupiter is famous for its chaotic weather, from tiny swirling eddies to massive storms like the Great Red Spot. But here's the odd part: there's a glaring gap in between. Where are the mid-sized storms? This absence isn't just a quirk, it's a clue that Jupiter's atmosphere operates by rules we don't yet fully grasp. One possible explanation is rapid upscaling. Imagine Jupiter's atmosphere as a cosmic blender, where smaller storms get caught in larger ones before they can grow to a middle size. The planet's fierce jet streams, some reaching speeds of 1,000 miles per hour, could act like conveyor belts, sweeping up smaller storms and merging them into bigger systems before they ever reach an intermediate stage. This would explain why we see plenty of small eddies and massive vortices, but nothing in the middle. The storms simply don't have time to stabilize at that size. But there's another intriguing theory: an invisible atmospheric filter. Jupiter's swirling clouds might hide mechanisms that prevent mid-sized storms from forming in the first place. Some scientists suggest that the planet's deep gravity waves, ripples in the atmosphere caused by differences in density and wind speed, could disrupt storms before they grow too large. These waves might act like a sieve, breaking apart storms that reach a certain size, leaving only the smallest and largest to dominate. Then there's the role of energy distribution. Jupiter's atmosphere is a battleground of competing forces, with heat rising from the interior and winds racing at breakneck speeds. This chaotic environment might favor extreme outcomes. Either storms stay small and fleeting, or they balloon into giants. There's no stable middle ground because the conditions are too volatile. It's like trying to balance a ball on a ridge. It either rolls back down or tips all the way over. The missing mid-sized storms also raise questions about how Jupiter's atmosphere compares to Earth's. On our planet, storms come in all sizes, from brief thunderstorms to sprawling hurricanes. But Jupiter's lack of intermediate storms suggests its weather follows a different playbook. This isn't just academic, it could help us understand gas giants beyond our solar system. If Jupiter skips the middle stage, maybe other giant planets do too. Juno's observations add another layer. The storms we do see aren't randomly distributed. They cluster in specific bands, hinting that Jupiter's latitudinal jet streams play a role in shaping storm sizes. Some regions might act like storm nurseries, while others serve as graveyards, breaking them apart before they can grow. What's clear is that Jupiter's atmosphere is far more selective than we imagined. Whether it's rapid mergers, hidden waves, or sheer energy chaos, something is filtering out the middle players. Solving this mystery could rewrite how we think about planetary weather systems, not just on Jupiter, but across the universe. Up next, we'll dive into another enigma: why Jupiter's inner layers spin faster than its surface, a discovery that challenges our understanding of how gas giants rotate at all. Now let's peel back another layer of Jupiter's mysteries, literally. Deep beneath its swirling clouds, the planet's inner layers are spinning faster than its surface, a phenomenon that defies expectations. Imagine a ball of liquid where the center whirls quicker than the outer edges. That's Jupiter for you, and this bizarre behavior might hold the key to understanding the planet's hidden structure. The evidence comes from NASA's Juno mission, which detected subtle gravitational tugs suggesting Jupiter's interior isn't rotating uniformly. While the visible atmosphere completes a full rotation in about 9 hours and 50 minutes, the deeper layers, thought to be a mix of liquid metallic hydrogen and helium, appear to spin a few minutes faster. This differential rotation paints a picture of a planet that's more like an onion with layers slipping past one another than a solid, unified sphere. But how does this work in a fluid planet, unlike Earth, where rotation is relatively consistent because of our solid crust? Jupiter has no fixed surface. Its outer layers are gaseous, while the interior is under such immense pressure that hydrogen behaves like a liquid metal. This creates a unique environment where rotation speeds can vary with depth. Think of it as stirring a cup of coffee. The liquid at the bottom moves faster than the froth on top, thanks to friction and viscosity. Jupiter's immense size and fluid composition amplify this effect on a planetary scale. One leading theory suggests that Jupiter's rapid inner spin is fueled by the planet's own magnetic field. The dynamo effect, generated by the motion of conductive fluids, could be transferring angular momentum inward, speeding up the deeper layers. Another idea points to the planet's formation. As Jupiter accreted material billions of years ago, the inner regions might have retained more rotational energy, while the outer layers slowed due to interactions with the solar wind or its own expanding atmosphere. The real kicker: this differential rotation might hint at a hidden, structured core. While most models assume Jupiter's core is diffuse or fuzzy, the uneven spin rates could mean there's a denser, more coherent mass at its heart. Imagine a dense nugget of heavy elements, like a buried anchor, influencing the flow around it. This would challenge the prevailing view that gas giants lack well-defined cores and could reshape how we model planetary interiors across the cosmos. What's more, Jupiter's inner spin could explain some of its other mysteries, like its lopsided magnetic field or the bizarre stability of its polar cyclones. If the deeper layers are moving independently, they might generate currents or waves that ripple outward, affecting everything from storm formation to auroras. It's a reminder that Jupiter isn't just a ball of gas, it's a dynamic, layered world with secrets still waiting to be uncovered. Up next, we'll explore another atmospheric oddity: Jupiter's cold spots, mysterious dark patches where temperatures drop unexpectedly. What's chilling these regions, and why do they defy our climate models? The answer might lie in the planet's auroras, or something even stranger: Now, shifting our gaze to another of Jupiter's puzzling features, let's talk about its so-called cold spots, dark, enigmatic patches where temperatures plunge far lower than scientists ever predicted. These regions are like shadowy voids in the planet's upper atmosphere, defying every expectation of how a gas giant should behave. While most of Jupiter's atmosphere blazes with heat, these spots are inexplicably frigid, creating a stark contrast that has researchers scratching their heads. The discovery of these cold spots came as a shock primarily because they appear where they shouldn't. Normally, Jupiter's upper atmosphere is warmed by the planet's intense auroras, which funnel charged particles toward the poles, creating heat. Yet, some of these dark patches sit right in the middle of these energetic light shows where temperatures should be at their highest. Instead, they're hundreds of degrees colder than their surroundings. It's as if you walked into a roaring bonfire only to find an icy pocket hidden within the flames. One leading theory points to auroral activity as the culprit, but not in the way you might think. While auroras typically heat the atmosphere, the swirling electrical currents they generate could also be carving out pockets of cold air. Imagine a massive whirlpool in the ocean where the spiraling motion drags cooler water up from the depths. Similarly, Jupiter's auroral currents might be pulling colder gases from deeper layers of the atmosphere into the upper regions, creating these anomalous cold spots. It's a delicate balance between heating and cooling, and somehow Jupiter's system tips in favor of chilling these patches. Another possibility involves gravitational waves, not the cosmic ripples from black holes, but large-scale atmospheric waves generated by Jupiter's turbulent weather. These waves could propagate upward, disturbing the upper atmosphere and redistributing heat in unexpected ways. Picture throwing a stone into a pond. The ripples spread outward, disrupting the calm surface. On Jupiter, these atmospheric ripples might be disrupting the flow of energy, leaving behind isolated zones of cold. What makes these cold spots even more baffling is their persistence. Unlike storms that come and go, some of these dark patches linger for years, resisting the planet's relentless winds and temperature fluctuations. Current climate models struggle to explain this stability, suggesting there's either a missing ingredient in our understanding of Jupiter's atmospheric dynamics or an entirely unknown process at work. Some scientists speculate that these spots might be linked to hidden structures deeper in the planet's atmosphere, perhaps vortices or chemical compositions that act like atmospheric refrigerators, actively cooling their surroundings. The implications stretch beyond Jupiter. If we can unravel why these cold spots exist, it could reshape how we study other gas giants, both in our solar system and beyond. For instance, Saturn's polar hexagon or Neptune's supersonic winds might hide similar surprises waiting to be decoded. Jupiter's cold spots are a reminder that even the most studied planets can harbor secrets that defy our best models, and that's what makes them so thrilling to explore. Up next, we'll dive into the chaotic dance of Jupiter's smaller moons, where orbits collide, swap, and even vanish. How does this gravitational ballet work, and what does it reveal about the solar system's violent past? The answers might be more dramatic than you think. Turning our attention to the cosmic dance around Jupiter, let's unravel the chaotic orbits of its smaller moons. Unlike the predictable paths of Earth's moon, Jupiter's retinue of tiny satellites behaves like marbles in a spinning maze, colliding, swapping places, and sometimes vanishing entirely. This gravitational chaos isn't just random, it's a window into the solar system's turbulent youth. At the heart of this pandemonium lies Jupiter's immense gravity. As the solar system's heaviest planet, its pull creates a gravitational battleground where even slight tugs from nearby moons or passing comets can send smaller objects spiraling into new trajectories. Take Himalaya, Jupiter's largest irregular moon, which travels in a lopsided orbit at a steep tilt. Its path suggests it was once a free-floating asteroid until Jupiter's gravity snatched it up, locking it into an unstable embrace. Meanwhile, moons like Ananke and Calm orbit backward, moving in the opposite direction of Jupiter's rotation, a clear sign they were captured rather than formed alongside the planet. Some of these moons play orbital musical chairs. The Himalaya group, a cluster of moons with similar orbits, might actually be fragments of a single ancient collision, their shared path a ghostly echo of that violent event. Even more bizarre are moons like Valetudo, discovered in 2018, which cruises through the orbits of other moons like a rogue train on intersecting tracks. Astronomers predict it could eventually smash into another moon, scattering debris that might form a new ring around Jupiter or get ejected from the system entirely. This chaos isn't just happenstance. It's a relic of the solar system's formation, when young Jupiter's gravity hurled comets inward and scattered protoplanets like bowling pins. Back then, space around Jupiter was a demolition derby with countless objects vying for stable orbits. Most were ejected or destroyed, but the survivors today's irregular moons bear the scars of that era. Their wonky paths are cosmic fossils, preserving clues about how Jupiter reshaped its neighborhood. Modern observations reveal even wilder scenarios. Moons like Pasiphae and Sinope loop so far from Jupiter that the Sun's gravity occasionally overpowers the planet's hold, stretching their orbits like taffy. Some may eventually break free, becoming Trojan asteroids trailing Jupiter at a safe distance. Others might veer too close to the gas giant and be torn apart by tidal forces, adding to Jupiter's faint rings. What does this mean for the solar system's story? These erratic moons suggest that planet formation wasn't a tidy process. Jupiter likely bullied smaller worlds, either absorbing them or flinging them into deep space. Some may have carried water or organic molecules to Earth, sparking life. Others might still wander the outer solar system as rogue planets. As we peer deeper, missions like the European Space Agency's Jupiter Icy Moons Explorer could uncover more lunar oddballs, rewriting our understanding of orbital mechanics. For now, Jupiter's chaotic moons remind us that even in the seeming order of the cosmos, a little anarchy persists, and it's that very chaos that makes our solar system so fascinating. Coming up, we'll examine Jupiter's controversial role as Earth's protector or menace. Does it shield us from deadly comets, or is it secretly flinging them our way? The debate is hotter than you might expect. Now let's shift our gaze from Jupiter's chaotic moons to a debate that hits closer to home: its role in Earth's safety. For decades, scientists have argued whether Jupiter acts as our cosmic guardian, deflecting deadly comets away, or if it's more like a gravitational pinball machine, sending them straight toward us. The answer isn't as clear-cut as you might think, and the latest simulations only deepen the mystery. Take the so-called cosmic shield theory first. Proponents argue Jupiter's massive gravity acts like a celestial vacuum cleaner, sucking in or flinging away hazardous comets and asteroids before they reach the inner solar system. A prime example is Comet Shoemaker-Levy 9, which Jupiter tore apart and absorbed in 1994. Had that comet continued toward Earth, the impacts could have been devastating. Jupiter's sheer size means it intercepts far more debris than smaller planets, potentially sparing us from catastrophic collisions. But there's a flip side, the pinball machine scenario. Critics point out that while Jupiter might catch some threats, its gravity can also perturb the paths of icy bodies in the Kuiper Belt or Oort cloud, nudging them onto trajectories that cross Earth's orbit. Imagine a game of cosmic billiards. Jupiter's gravitational kick might send a harmless, distant object spiraling inward, turning it into a potential hazard. Some studies suggest Jupiter's influence could even increase the rate of comet impacts on Earth by up to 30% over long timescales. Recent computer simulations add fuel to the fire. One model showed Jupiter deflecting 60% of incoming long-period comets away from Earth, supporting the shield idea. but another study found that Jupiter's gravity destabilizes asteroid orbits in the inner belt, increasing collision risks for rocky planets like ours. The contradiction lies in the types of objects studied. Jupiter may protect us from some comets but expose us to other debris. Then there's the wild card, Jupiter's moons. Europa and Ganymede's gravity can subtly alter the paths of passing comets, creating unpredictable ricochets. A comet that might have missed Earth entirely could get a last-minute nudge from a moon's pull, putting us in the crosshairs. It's a reminder that Jupiter's system is so complex. Its role in Earth's safety isn't just about the planet itself, but its entire gravitational entourage. What does this mean for Earth's history? Some researchers credit Jupiter with creating stable conditions for life by clearing out early solar system debris. Others blame it for past mass extinctions, like the asteroid strike that wiped out the dinosaurs. The truth likely lies somewhere in between. Jupiter isn't purely a hero or villain. It's a force of nature with consequences we're still untangling. As missions like the European Space Agency's Jupiter Icy Moons Explorer probe deeper into the gas giant's influence, we may finally get clarity. Until then, one thing's certain: Jupiter's relationship with Earth is far more nuanced than a simple shield or threat. It's a dynamic interplay of chaos and protection, reminding us that in space, even safety is a matter of perspective. Coming up, we'll look ahead to the unsolved puzzles future missions might crack. From the secrets of Jupiter's interior to the enigmas hiding beneath its moon's icy shells. The next chapter of Jupiter's mysteries promises to be as thrilling as the last. Just when we think we're starting to unravel Jupiter's secrets, the next wave of cosmic detective work promises to rewrite the playbook entirely. Upcoming missions armed with cutting-edge technology are gearing up to peel back the layers of this gas giant's greatest mysteries, and along the way, they'll likely stumble upon questions we haven't even thought to ask yet. Leading the charge is the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, set to arrive in the Jovian system by 2031. This mission has its sights set on Ganymede, Callisto, and Europa, 3 moons hiding vast subsurface oceans. But here's the twist: JUICE won't just skim the surface. It's equipped with ice-penetrating radar capable of mapping these alien oceans in unprecedented detail. Imagine discovering currents, tides, or even hydrothermal vents beneath Europa's icy crust features that could redefine our search for life beyond Earth. And Ganymede, the solar system's largest moon, has its own magnetic field, a rarity. JUICE will investigate how this moon generates its magnetism and whether its ocean interacts with Jupiter's colossal magnetic bubble in ways we've never seen. Not to be outdone, NASA Europa Clipper is on a focused quest to crack Europa's enigmas. Slated for launch in 2024, this spacecraft will perform dozens of close flybys, analyzing plumes erupting from the moon's icy shell. These jets might carry samples of the hidden ocean, offering clues about its chemistry and potential habitability. But the real curveball: Europa Clipper's instruments could detect organic molecules or even indirect signs of biological activity. It's a long shot, but if there's ever been a place to look for extraterrestrial life, Europa's dark, salty depths are it. Then there's the puzzle of Jupiter's interior. Despite Juno's revelations, we still don't know how deep those raging jet streams go or whether the planet's core is a diffuse soup of heavier elements. Future missions might deploy atmospheric probes designed to plunge deeper than ever, braving crushing pressures to measure the planet's composition. Picture this: a probe discovering layers of exotic matter, metallic hydrogen, helium rain, or even denser phases of water that defy our current physics textbooks. And let's not forget Jupiter's magnetic field. It's a monster stretching millions of miles and pulsing with auroras that dwarf Earth's. Upcoming studies aim to map its finer structures, especially near the poles where Juno spotted those baffling hot shadows. Could there be unseen currents or magnetic reconnections powering these phenomena? the answers might unlock secrets about how gas giants across the cosmos generate their magnetic shields. But here's the kicker: every time we solve one Jovian riddle, another takes its place. Missions like JUICE and Europa Clipper won't just deliver answers, they'll hand us a new set of mysteries. Maybe we'll find that Europa's ocean is more dynamic than imagined, or that Ganymede's magnetism hides a chaotic core. Perhaps Jupiter's winds run deeper than any model predicts. One thing's certain: the next decade of exploration will remind us just how little we truly understand about this gas giant and its entourage of frozen worlds. As we wrap up our journey through Jupiter's unsolved puzzles, it's clear this planet isn't just a celestial curiosity. It's a living laboratory challenging our assumptions at every turn. From its storm-racked skies to its hidden oceans, Jupiter keeps its secrets guarded well. But with bold missions on the horizon, the greatest revelations may still lie ahead. What an incredible journey through Jupiter's greatest enigmas, right? From the moment we peered into the churning chaos of the Great Red Spot to the mind-bending auroras crackling over its poles, this planet has handed us puzzle after puzzle. Think about it: storms larger than Earth that rage for centuries, a magnetic field that twists science fiction into reality, and hidden oceans beneath icy moons that could rewrite the rules of life itself. Every discovery peels back a layer, only to reveal something even stranger underneath. Take Jupiter's core or lack of one. We expected a dense, rocky heart, but Juno's data suggests it might be partially dissolved, almost like cosmic soup. Then there's the water mystery. A gas giant should be soaked in it, yet Jupiter seems oddly dry. Is it hiding beneath storms, or did its formation story play out differently than we thought? And let's not forget those geometric cyclone clusters at the poles, defying every model by refusing to merge. It's as if Jupiter whispers, "Your textbooks. Throw them out." But here's the real kicker: Jupiter isn't just a spectacle. It's a guardian, a sculptor of the solar system. Its gravity either shields us from comets or flings them our way. Scientists still debate which. And those bizarre radio signals, they're not just noise. They're clues to how magnetic fields dance between Jupiter and its volcanic moon Io, a cosmic tango we're only beginning to decode. Now, as missions like JUICE and Europa Clipper gear up, we're standing on the brink of even bigger revelations. Imagine if Europa's plumes carry traces of life, or if Ganymede's magnetic field hides a churning ocean of liquid metal. The next decade could redefine what we know about not just Jupiter, but the very nature of planetary systems. So here's my question for you: which of Jupiter's mysteries left you the most stunned? Was it the shrinking Great Red Spot, the eerie, hot shadows, or something else? Drop your thoughts in the comments. I'd love to hear what fascinates you most. And if you're as hooked on these cosmic riddles as I am, don't forget to hit subscribe and ring that notification bell. The universe has a way of surprising us, and you won't want to miss what comes next. Until then, keep looking up. The greatest discoveries are still out there waiting.